everyone. Welcome to PCB Chat, where we talk with experts across the printed circuit design, manufacturing, and electronic supply chain fields. I'm Mike Buetow, Editor-in-Chief of PCD&F and Circuits Assembly. First, a word from today's sponsor. This podcast is brought to you by Turnkey Pro from Sierra Circuits. What if you could source your components, upload your specs, and receive an instant quote in less than 15 minutes? What if your designs could be fabricated and assembled and delivered to your door in 5 days with a guarantee of 0 defects? Then try Turnkey Pro from Sierra Circuits for your next design and use promo code PCB Chat to receive $200 off your next order.
At PCD&F, we are always on the lookout for aspiring new contributors, and we really scored this year with today's guest. Those who read the magazine or see us online at PCD&F.com have probably come across Terry Jernberg, the face of a new column this year under the eponymously named Jernberg PI. The title harkens back to Magnum PI, the popular detective show of the 1980s. And it is, of course, a play on Terry's last name and his subject matter, power integrity. We like to think of Terry as our own investigator of noise and timing problems in the power delivery network. Terry, thanks for joining us on PCB Chat.
Thanks, and thanks for having me. It's a topic I really enjoy talking about, and there's a lot of information we can get out there.
Let's start with your background. You've spent much of your career in the trenches, so to speak, at EMC and Bose, correct?
Yeah, I've actually split my career kind of. I've spent half of my career actually supplying tools and working for tool companies, and then the other half of it actually as a user of tools. So kind of supplier and demand. I've switched back and forth, literally back and forth from tool to user to tool to user, and gives me a kind of a good perspective on both the pains of either side.
For about 20 years now, signal integrity has been front and center among electronics design problems. But in the past few years, PI has joined it. What's happened during that time to make the picture more complex?
I actually don't think anything in particular has changed so much. The reality now is what we used to ignore and what we used to consider as the ideal power plane and the ideal return path just through miniaturization and through advances in manufacturing and new packaging techniques and just the overall density of things, what used to be ideal is no longer ideal. So signals have always traveled in a loop. Electricity never, hasn't really changed. It's just now that, things that we used to ignore now are, we've refined the other aspects of signal integrity so much that these things are now the big bubble. And now that's what we have to go after.
I have a couple of Bose headsets myself, and once in a while I take things apart as I replace them with new things, or if I'm being honest, maybe my son breaks one, and so it actually just gives me an opportunity to take everything apart. That must have been a great experience for you insofar as seeing firsthand what some of the effects are. I mean, they're using some of the tightest configurations imaginable.
Absolutely. And they have some fantastic engineers there, and they really are pushing some of the edge of technology. And the other thing about that is they had a very diverse product line. They had home entertainment things, automotive product lines, and really the signal integrity branched out to all those types of areas. So it really got a kind of a wide breadth of exposure to things. The other kind of interesting part of that is, when you think about the noise canceling headphones, and everybody's, adopted them and become very comfortable with them, that essentially conceptually is exactly what we're doing with equalizers and all the high-speed signal stuff. We're creating the opposite of noise and sticking it onto the signal. So it's kind of dovetailed into, what we do on regular data communications now. So it gives me a good example of, and kind of a good reference to describe what's going on in the electrical world. People understand it when they have their headphones on.
In a recent column of yours titled The Case of the Noisy PDN, you talk about resonance and how resolving it as you would an SI problem isn't necessarily the way you would approach it. Why is that?
Well, when we think about signal integrity, we know what the signal is. We're really trying to take that edge and we're trying to follow it over its path from driver to receiver. But when we think about power integrity, it's not a single edge or a single signal or a single frequency. These things are all kind of being transmitted all collectively, on the same conductors. So we approach it very different. Instead of trying to match impedances the way we do in a signal integrity line, 50 ohm to 50 ohm to 50 ohm, we take a different approach. We try to keep that impedance low over a very wide frequency range. Essentially, that lets us keep the path very clean regardless of what type of signal it encounters. So it can be transmitting high frequency signals and low frequency stuff all on the same path, the same conductors. There's just no, because the impedance is so low, there's no ability to generate a voltage at those frequencies. So essentially, we've smoothed the path for all frequencies. It's a different approach instead of actually targeting a frequency and smoothing the path for that target frequency the way we would do in a SI approach.
I think you likened it in that column to an echo or a wave, something like that.
Yeah, it's similar to when you think about it, like the if you throw a rock into a pond and you can see the ripples and they propagate in every direction, or a raindrop for that matter. I think I put a graphic in there, something like that. But in reality, each time a signal edge hits that power plane, it generates that type of ripple that propagates on our planes. It propagates in all directions instead of just down the conductor in a transmission line on a transmission plane. It propagates out in both the X and the Y direction. So these things intersect and they interrupt each other, and sometimes they combine and are collective and make the matter worse, and other times they cancel each other's out. It just is impossible to predict that because it changes over the course of the board actually functioning. So, at some point in time, things that were contributing in a negative way, maybe contributing in a positive way. So we just can't count on that. We can't do things based on, a snapshot in time. We have to smooth things for all frequencies for any period of time.
You've noted in your work that power demands are rising, and PDNs need to be capable of supplying current demands of high-speed signals. I don't think anyone would disagree with that, but you also say, and this is a quote, "While all this may suggest a more robust PDN is needed, often the opposite is true." What do you mean by that?
Well, I think we tend to put a ton of copper in and we try to overkill things, and we can create things like capacitive loading and battery problems and even conductive paths. Instead of planning, sometimes we actually flood stuff with copper. And more often than not on boards, I've seen them come along and they just put copper all over the outer layers or copper grounds. And it actually can create some path problems. It can create some interceptions, and it can also create exposure to the outer layers where we had ground currents contained and directed. It's now exposed to the outer layers and now off into the antenna world where we have to qualify our devices. So it just becomes a contained problem. We've sort of opened the gates with extra copper, and part of this is due to just not planning. We're doing extensive amount of planning in terms of how we're going to route our etch, and we're just going to assume that the return paths are going to come back, and match up. And when we think about, the task of routing, it's a lot harder to create the paths for a plane than it is to create, a signal trace, even a bus. So, what we're advocating is to get those planes in, to get the power layers down, put your return pass in, and then route your traces against that. It gives you a canvas, if you will, to route your traces against. And then we get back to that situation we had years ago that you asked me about earlier, the ideal power plane. We get back to that, sort of emulating that type of scenario, and we can move on in our SI world.
What are some of the more common complaints or problems that customers come to you with?
Probably the biggest thing we see, again, has to do with this return path situation, where people have become confident, and rightfully so. The simulators have become really accurate. The field solvers are quite good. We're getting very good measurements, on our signal integrity simulations, and people get confidence in that. And then they build a board, and the board comes back and it doesn't match. And the immediate reaction is, well, there's something wrong with my SI simulation. And more often than not, that is a problem in the power plane. It's the scenario that they've routed over a split plane, or that there's extensive noise on the power plane, or density issues, or just basically problems that go back to that just wasn't included in their simulation. So the difference in what people get nervous about and what they actually start to doubt the SI simulators on is the return path aspect of it. They're not simulating the entire loop, so they're not seeing or even accounting for these return path considerations. And more often than not, we see that in the memory side, because when we look at simulating wide buses, serial links, it's okay. We're extracting that, we're including that in the return path in that type of simulation. But very often on the buses, particularly with DDR and memory, we're simulating the entire bus, but we're not including the return path. We're back to that ideal return path mentality, and that's not the reality anymore. So that accounts for a fair amount of the deviations, and people start to lose confidence in their simulator.
You mentioned simulation. Would you agree that one of the real changes in printed circuit design, perhaps since the beginning of your career, has been the increased need for analysis on top of all the traditional routing and placement requirements of the job?
Yeah, and I think the acceptance of it. Engineers like measurements, so the fact that we can now get some correlation between the measurements and the tools, and that we can actually complete that picture, I think that has made a huge leap for people having confidence in the tools to essentially transition from using the tools as an analysis phase to using them to make decisions in design. And I think that's really probably the biggest thing that I've seen, is instead of saying, okay, the board is done, let's see how we did and simulate it, people are actually using it in advanced stages to figure out how they're going to route, to figure out what the stack ups are going to be, but to actually use it as a design tool instead of just an after the fact analysis, is it good enough kind of tool. And I think that's a real migration. And I think it's poised for another step in that direction when we look at things like equalizers. We're about to make the next leap where we're going to use artificial intelligence to kind of dial in what the constraints and the parameters that we could guess at for a week, but we can now, use AI to kind of narrow that down. So we do the best we can on the physical board. We use the artificial intelligence to narrow down those parameters, and that's what's allowing us to push these speeds that Moore's law said over and over again we couldn't do, and people keep doing it.
You're raising the issue of the software tools and what their function is relative to the designers or the engineer's actual knowledge. In your estimation, how much of resolving PI problems comes down to the engineer simply knowing what they're supposed to do versus what the tools are sort of helping them or leading them to?
I think there's widespread knowledge both in the engineering world and in the PCB design world, and those worlds really blend. And I think the knowledge is there. I think what can be overwhelming is just the sheer scope of this. To be able to look at literally thousands of nets on a board and find the place where it went over a split, or find the place where these nets ran parallel for too long. So I think it's a matter of scale. I think everybody knows the problems that exist, and I think they comprehend that. So I think the ability to find those problems and almost triage type of that, to look at an entire board and say, okay, these nets of this area, I really have to do the extensive deep dive SIPI simulation. These areas, rules of thumb are good. And these areas, I can do some geometric checks, and that's going to be adequate. And that sort of scaled approach is the only way we're going to be able to meet both the challenges of the product reduction and the time cycle. We could analyze these boards and build one every 3 years and have them perfect, but that's just not the way business is running anymore. It's just they got to go out quick. You need a decent answer today instead of a perfect answer in 2 weeks. That's what some of the scanning tools and some of the sort of scaled approach is leading towards. It doesn't give up anything. We're not going to miss any mistakes that we had otherwise. We just may do some geometric checks that drive us to areas that we have to actually go further and actually do the mathematical analysis. But it'll be a layered thing. But without a doubt, we can't just assume anything's perfect anymore, because the construction just doesn't reflect that.
Great points, Terry. Our guest today has been Terry Jernberg of EMA Design Automation. Read his column, Jernberg PI, each month in PCD&F. Terry, thanks for joining us.
Thank you. I enjoy talking about this, and just have some great questions. I hope people can get their hands on this, and don't be afraid of it.
If somebody wants to reach out to you, how do you recommend they get a hold of you?
Absolutely. We're actually putting some contact stuff up. We're going to publish some additional things up on the EMA webpage. That's probably the best way to get through the navigation part of it, but also it's the best way to get access to some of the additional material that we're coming up with and see some of the product stuff that's offered, that we support. But really, all of these tools are good. Whatever tool set you have, dig in and start to use it a little bit. They're all good. This stuff isn't hard. It's just really volume. I think we got a great start in the PCB world. They navigated a lot of other things. This is just one more input in the pile.
Great. Thank you, Terry.
This podcast has been brought to you by Turnkey Pro from Sierra Circuits. Turnkey Pro is the simplest platform for sourcing all your components, uploading specs for fabrication and assembly, and receiving an instant quote, all online in fewer than 15 minutes. Try Turnkey Pro by Sierra Circuits today and use promo code PCB Chat to receive $200 off your next order. For PCB Chat, this is Mike Buetow. Have a nice day.